of massive galaxies and black holes.
Okay, thank you. It's a pleasure to be back here every year to join the conference. And today I'd like to give an update on the status of the massive survey, which we started in 2013 to study the 100 most massive galaxies within distance to 100 megaparsecs distance out to COMA. The 5 core members are Jenny Green, Jens Thomas, Nicholas McDonald, John Blakesley, and myself. And quite a number of Berkeley graduate students, undergraduate students have been involved. And we also have a number of sort of parallel programs going on using multi-wavelength and spectroscopic and photometric efforts. We got HST data, we have a CO molecular gas survey going on, and warm gas barrages here, and X-ray studies, and we also have radio data in hand. And as we speak, Drew Newman is at Magellan taking long slit data for IMF studies. So I would like to just highlight a few results today. Very quickly, our sample selection was meant to be kept simple. The goal is to study the assembly history and the environments of the most massive galaxies and their central supermassive black holes. So the sample is stellar mass selected. So they are all very massive, more than 10 to the 11.5 solar masses in stellar mass. And we use the K-band absolute magnitudes from 2 mass to select them. So it's meant that there are no cuts on velocity dispersions or radii or anything. It's just stellar mass and volume limited to 108 megaparsecs, chosen to include COMA. So the few famous clusters in our sample are Virgo, Perseus, and COMA clusters. And morphology, we limited this to early types, ellipticals or S0s. So it's all the entire northern sky. And so you can ask how many of these are in the Sloan footprint, for example. And about 70% of our galaxies have Sloan photometry. But when you ask about spectroscopy, only about 20% of them have SDSS spectrum. And again, SDSS is just a 3 arcsecond fiber. And we are, as you will see, it's an IFU survey, so we are going out to 110 arcseconds. And a few other conditions. We don't want to target very close neighbors because it would be hard to study the kinematics of individual ones. Of course, they themselves are interesting objects. So today I would like to just highlight the diverse environments lived in by these massive galaxies. We tended to talk about halo mass, how they map into stellar masses, and environments. We've heard a lot about environments today, but I just want to highlight that these 100 nearby most massive galaxies, only 9 of the 116 galaxies we're targeting are massive enough to make into our sample, and only 9 of these are in these 3 famous clusters. Okay? And 26 of these are labeled isolated in quotes in the 2-mass redshift catalog. And obviously, it's only down to the shallowness of the 2-mass magnitude limit. So they obviously have probably fainter satellites, we're sure. But within the 2-mass catalog, they have no more than 3 members, according to a Friends of Friends linking group catalog due to John Hokra and collaborators. And again, virial masses, these are based on the good old velocity dispersions of galaxies. And so they're quite uncertain, but that's our only handle on the halo mass, and they range from 10 to the 13th out to the COMA cluster, 10 to the 15th. So over a range of 100, despite the fact that our stellar mass range is about 3, because things just don't go more massive than COMA galaxies. Okay, and in terms of centrals versus satellites, one can ask that question. For the sort of smaller halo part of our sample, all those galaxies in these groups are the brightest group galaxies, so they're the BGGs. But the more massive end of our, the halo mass of our galaxies, only 50% of them are actually the brightest galaxies, meaning the other half are satellites in these groups, but they are bright enough to be in our sample. Of course, their brightest cluster is also in our sample. Okay, so just overall, we have centrals. Most of our galaxies are centrals, but we also have satellites in groups, and also 26, they are in probably very small groups. And just a current status, to sort of highlight some of the observations that we have been conducting over the past 3 years. The core of our observation is based on the Mitchell virus P IFU, which is a wide field IFU on the 2.7 meter McDonald telescope, and it has 246 fibers. So in one shot, we get 246 spectrum over almost 2 arc minute field of view. This is one of the largest field of view IFU available. And each fiber is very wide, so the diameter is 4 arc seconds, very comparable to the Sloan fiber. So Sloan would have information only at the very center. And but we would like to get very detailed studies of the interior structure out to 2 or 3 effective radii for each galaxy. So we have in hand now data for more than 75 of the galaxies. Our goal is to go to 116 selected by the mass criteria I just described. But we also follow up on a subset of these galaxies, the suitable ones, that we go into the very central part and we zoom in with 8 to 10 meter telescope IFUs. And the goal here is to get spectroscopy of the very inner 5 arc seconds or so with resolution down to a fraction of an arc second. And these data are critical for measuring supermassive black hole masses. We use, because we would like to resolve the severe influence of the black holes. But we also need the wide field kinematics for us to get the sort of anchor for what the stars are doing in the dark matter in the black holes when we do the modeling. And just very quickly, we also have parallel photometry and other wavelength observations going on. We got HST data for the central light profiles of some of our galaxies. Many of them do not have archival data. And we really want to, we need the central photometry also for the black hole mass modeling. And also, as I will talk about, whether the central light profiles chord or cuspy power law is a very important feature of these massive galaxies. And photometry-wise, the 2-mass catalog is very, very shallow. So we have ongoing CFHT deep K-band imaging going 3 magnitudes deeper of each galaxy in order to get the outer halos. We would like to get the effective radius, magnitude, and these properties much more accurately than what 2-mass can do. And we also have our radial observations and X-ray archival studies. We got some Chandra data for new observations too, and VLA studies of AGN activity at the center. So I just want to highlight sort of 3 results today. The first one I'd like to talk about are the most massive black holes, which is one of the primary goals of this survey, is to provide a homogeneous, well-selected galaxy sample for us to get the black hole masses. And I just want to, again, highlight this M-sigma relation. There have been a few updates to our 2013 compilations with several more data points, but the general trends are the same. I just want to go to and this is over 4 magnitudes of in black hole masses from the Milky Way all the way up to M87 and others. So this is 10 to the 10 billion solar masses up there and at high velocity dispersions. So prior to our survey, very few, in fact, M87 was the record holder at the high mass end. And the reason is that massive early type galaxies are rare, so you got to probe a larger volume before you can find more of these. And there's a very important second reason for why these observations require different techniques from the remarkable Nuker team's efforts. The reason is these massive galaxies have basically no light at the center. They're extremely cold in surface brightness, as Sandy had told us more than a decade ago. And so you need really high signal-to-noise spectra, then you really need 8 to 10 meter telescopes rather than the HST. But you still also need to resolve the sphere of influence. You need high spatial resolution. So we need either AO data or fantastic natural scene conditions to measure the black holes. And we started the massive survey to have a comprehensive sample of galaxies to select from. So I just want to talk about this massive end, again, of the black holes, that what do we know now beyond M87? Okay, again, for 3 decades, M87 was the record holder as the most massive black hole. And the mass measurements, the most typically commonly quoted is the 6 billion solar masses based on stellar mass measurements. And in 2011, my former student, Nicholas McConnell, and us, we had a study. We looked at the obvious galaxies. If you want to find big black holes, you look at the biggest galaxies, and these tended to live at the centers of rich clusters. So COMA's brightest cluster, NGC 4887, but these are much more distant. This is at 102 megaparsecs rather than 16.7 or whatever. So they're much harder to observe. And the Leo cluster is yet another quite rich cluster. Its central galaxy is NGC 3842. So these were the two that went beyond 10 billion solar masses. But you can see 4889 is a quite complicated system, so our error bars were quite large for that black hole. So since the massive survey, we recently reported the NGC 1600's black holes mass in a Nature paper in April this year, led by Jens Thomas, who did the orbital modeling for the black holes, for this black hole. And this target was part of the massive survey, but NGC 1600 is not nearly as massive as 4889, but it's massive enough to be in our survey. But the interesting thing about this galaxy is it's not living in a rich cluster. It's in a moderate galaxy group. It is the brightest group galaxy. In fact, it outshines its neighbors by more than a factor of 3. So it's almost like a fossil group. Okay? And this is a much simpler system, and we got very good data, so the error bars are quite small. So this is a 17 billion solar mass black hole. I'll talk a little bit about this in a moment. And I just wanted to highlight, since April, we got enough courage to now study 4874, which is the twin of 4889, the two almost comparably bright cluster galaxies in COMA. And this is a non-BCG because of 4889 wins. And, but it has even less light than NGC 1600, so you really need a lot of data for that. Our data are now looking quite good, so we are trying to narrow down the range of the black hole because we got to sample the stellar mass to light ratio black hole, and dark matter halo is a big grid. We're doing very time-intensive short orbit modeling, but it's at least 10 billion solar masses, and it's no more than 20 billion. We're still trying to work on pinning down the error bars here. But I just want to, and so stay tuned. We should get a number. We have a number, but I'm not quite confident to quote it yet. But I just want to, again, come back to 1600, so the environment discussion right now. That, again, just to remind you that the COMA cluster is an extraordinary object. It is the most massive cluster, in our local universe. Halo mass, depending on how you measure it, is 10 to the 15th-ish, a few times that, depending on if you use weak lensing or whatever, or X-rays, or galaxy dynamics. The X-ray luminosities are extraordinary, and the rank 2 galaxies, as I mentioned, 4874 is nearly as bright as 4889. Okay? And now we have measurements for both of these. But 1600, its halo mass really is about 10 times less. Okay? It's in a group. Its X-ray luminosities are 1,000 times lower, according to Chandra archival data. And its rank 2 galaxies, I mentioned, is much, much fainter. In fact, it's fainter than a usual group. That's what a fossil group usually is, when the dominant galaxy outshines its neighbors. And the distance is actually 50% closer, and this is relevant for the short radius I'll talk about momentarily. Okay? So it's striking that we got two comparable mass black holes, 4889 and 1600, but in two very different environments. Okay? So again, I want to come back to the sort of the central surface brightness profiles of these galaxies. Okay, so the surface brightness versus the radius of each galaxy. And these are taken from Todd Lauer's the nuclear team's fantastic HST data. But we plotted these, highlighting these galaxies I was talking about, which host the most massive black holes. So again, these are the power law, run-of-the-mill galaxies. And these giant ellipticals, as you can see in this absolute solar luminosity per square parsec units, they have very, very diffuse cores. And you see M87 here, this is 4472, and these are the two 10 billion solar mass ones I talked about. 1600 is our recent measurement. And the reason we shied from analyzing 4874 is because it has even less light here. Okay. But I want to, again, emphasize the striking bend over of the surface brightness profiles and this characteristic core radius. So 1600, for example, has a giant, giant core, okay, 0.7 kiloparsec, 2.3 arc seconds. And what is causing this core? Well, there are various theories in the literature. maybe binary black hole core scouring, kicking out stars on their radial orbits, therefore creating, this is a stellar light profile. Okay, there's a deficit of stars at the center. Or maybe black hole recoils after merger. Or I would like to propose, AGN feedback. Maybe you can kick out some of the gas that later on form stars. Okay, there are various scenarios, but observationally we can measure this core radius. Right? This is just purely based on HST photometry. Okay? So in the Thomas et al. Paper, we plotted two radii here and found this relation. So these are sample of 21 cored elliptical galaxies with dynamically measured black hole masses. Okay. So in the x-axis is just that break radius. However you measure it, it doesn't really matter. Here we're using core-Sirsic profile. Newkirk profile will give you a slightly offset, but the correlation is as tight. Okay. So this is purely based on photometry. This is a core radius. The y-axis, so the x-axis had nothing to do with black holes. Right? It's just a stellar mass profile. The y-axis is the sphere of influence radius of the black hole. Because we know the measurements, this is by our team and other teams, but we know these dynamical measurements. So we can actually compute the radius within which the stellar mass and the black hole mass equal each other. And this is the definition of the sphere of influence. Okay? So we plotted that on the y-axis. And this is where these 21 known black hole core galaxies lie. And the dotted line is 1-to-1. And the red line is our best fit. And it's statistically the same as the two radii being equal. Okay, so not only is the slope 1, there's no offset in this amplitude. It's really 1-to-1. And the intrinsic scatter is only 0.17 dec. So we think this is probably the best evidence right now supporting the theory that the cores are caused by black holes. How? I'm less willing to bet on that. I think binary scouring is still very, very good theory. AGN, again, is due to black holes. Okay, so the black hole is doing something to imprint this characteristic radius that causes this amazingly tight correlation. So just some thoughts about NGC 1600. So it is the first extreme black holes measured outside of rich cluster. Okay, and its black hole mass is about 2% of the stellar mass. And as you know, the mean relation for black hole and bulge mass is about 0.2% or 0.3%, depending on whose correlations you look at. So this is almost 10 times more massive than its bulge predicts. And sigma relation, same thing. It's way massive compared to its sigma. Okay, and the event horizon I want to come back to, and the Milky Way has 10 microarc-second event short show radius project on the sky. And of course, the Event Horizon Telescope is gathering data, trying to image the event horizon, the shadow of the black hole. And these are their two targets, M87 and Milky Way. And M87 is more distant, but it's much, much more massive. Okay, and it's interesting that NGC 1600 has a comparable, depending on which black hole measurement you use for M87, event horizon angular size on the sky. So I think this can be a potential, and other black holes we measure can be potential candidates for that telescope. And then one can ask, what is the link of these supermassive black holes to the luminous quasars? Right? Are they descendants of these quasars? Well, I think NGC 1600 is the first one that doesn't live in Coma, Leo, the Virgo cluster. And people have looked at clustering strengths of quasars at redshift 2, the 15 most luminous ones. It doesn't look like their halo masses are that different from the mean halo mass for quasars. So maybe 1600 is a descendant of one of these, quasars that may not have lived in a supermassive, halo mass. Okay, so right now we don't know if NGC 1600 is a rare find or is a tip of an iceberg, in the sense that Coma is rare. There are just very few things like Coma. So 4889 is rare. Okay? But 1600 is in a virial halo that's 10 times less massive. They're much, much more abundant. So we don't know if other similarly sized halos may host also extraordinary black holes, or maybe the magnitude gap was important for the central galaxy to eat enough to feed its black hole. Then that would be more rare. So the massive survey should answer this question. Okay, and again, this new scaling the scaling law that the two radii are statistically the same we're pretty excited about that relation. Okay? So I just want to highlight one other result from the massive survey, not related to the black holes, but rather from our large format IFU data, and then I'll just conclude. Okay? So we are ready. My graduate student, Melanie Veal, this paper is about to go in press, looked at the brightest sample 41 that we have Mitchell data, the wide field data for. So these are the angular momentum profiles for each one of these galaxies, and NGC 1600 is one of these. Okay, and this is the standard lambda versus ellipticity of the galaxies that the Alice 3D teams have plotted a lot for various galaxies. And you can see that most of our galaxies in this mass range, this magnitude range, are slow rotators. But we do have some fast rotators, okay? And the environments are not quite clearly correlated. Among the 7 fast rotators, those are the different kind of galaxies they are. Okay, but the fraction of slow rotators, these are Alice 3D points. They run out of galaxies here. So we fill in this very important bright end where you can see the slow rotators taking over. Okay. The last thing I'll show related to the lambda profile, since we have IFU data, we have all the spatial information, is the second moment, right, the sigma now. So lambda is really just the rotation normalized by sigma, but here is the actual velocity dispersion profiles of these galaxies. Now we actually have Melanie just made this plot, so there are 72 galaxies now in this sample. Okay, and in the top panel is the BGGs, brightest galaxies, and satellites, and isolated galaxies. I just want to highlight that the sigma profiles are not all isothermal, obviously. Okay, the BGGs, many of them actually have rising sigma. They get higher at the outskirts. Satellites are a mixed bag. And the isolated galaxies all have declining profiles. And I know the SLUX team have fantastic data for fewer galaxies out to about 5 to 6 RE. So I think it's interesting to look for these environmental trends. And I just want to mention that the 3 coma galaxies in our survey, the 3 brightest ones, all have strikingly rising sigma profiles. Maybe they're reaching the coma dark matter halo or something. Okay, we're still doing the mass modeling for these. So let me just go to the end by summarizing, by listing the publications of the massive survey that we have stellar population gradients. We heard quite a bit about that this morning. Jenny Green's paper studied that gradient for our sample of galaxies. About more than a quarter of our galaxies show CO emission lines. Okay, so we have some nice ALMA observations now of CO disks. And then the Andy Goulding's paper, we study X-ray hot halos of a subset of our galaxies with archival data. And a lot of them show extra heating above virial equilibrium. And I'll be happy to talk to you about. Okay, and there are a lot of papers coming up. And like I emphasized, I'm pretty excited with the IMF measurements that Andrew Newman is getting right now at Magellan. And we can get a wing 4 band here. What we do with that, I don't know. But Sandy asked me last time, do we have those lines now? He got 12 galaxies the past 2 days already. So hopefully we can study the very important IMF variations in these massive galaxies. Thank you.
The next speaker can come get ready and time for 1 or 2 questions.
Chung-Pei, this is not exactly a question about your work, but more on the interpretation. So there's a recent paper by Shankar, Mariangela Bernardi et al. That argues that since it's so much easier to find massive nearby supermassive black holes than the lower mass ones, that one has to be very careful about analyzing the data and determining things like the relationship between the supermassive black hole and its host galaxy, and that people who did simple-minded analyses, for example, the Cormany and Ho review, are deriving results that are wrong by a factor of more than 3. Any comments?
Yeah, I would just say that it's a very controversial study among the community. And
no, that's why I wanted to get your advice.
We'll turn off the video and then we'll talk. Dinner, how about we'll talk? Yeah. I just point out that Göttingen, the 2012, whatever, yeah, 07 paper, they did include upper limits in their analysis, and other people have. and they found different results. So I think that's very interesting. Yeah.
Well, I don't think they're questioning the results that you have. It's more a question of how to correct for any biases.
Right. So I think that's partly why we wanted to have the massive survey, right? Because in the past we went for
Always good.
right. So
You
but
don't have to worry about how to correct it.
that's right. So here at least we have a well-selected galaxy sample. So I think we know our sort of selection in fact. So then once we finish this survey with the 20 more black hole measurements, I think that's the first time it's not a heterogeneous sample. Then I think we should be able to address that question.
All right, let's thank our speaker again.